In this session, we discuss about the floating point formats. The floating point format has its advantage over fixed point in that it increases the dynamic range. Floating point can be considered to be similar to the scientific notation. The general format for floating point numbers may be represented as m into 2 to the power of e. 2 represents that the number is base 2. M will be the mantissa and E will be the exponent. So M is called as a mantissa or the fractional part in Q format and E will be the exponent. The mantissa and exponent both are signed numbers. Let us assume that we are considering a 12-bit for the mantissa and 4-bit for the exponent. Then the format will look something like this. Initial 4 bits will be the exponential bits and the remaining 12 bits represent the mantissa. We observe that the most significant bit in both the fields represents the sign and the remaining will be the magnitude. The respective weights are also represented here. Now, since the 12-bit mantissa is limited to the range between -1 to +1, the number of bits assigned to the exponent will control the dynamic range. The bigger the number of bits designated to the exponent, the larger will be the dynamic range. So mantissa has no role to play in the dynamic range. Everything is under the influence of the exponent. The number of bits for the mantissa defines the interval in the normalized range. In the previous diagram, the interval size is 2 to the power of -11 in the normalized range. The size is definitely smaller when you compare it with the Q15 format. However, when more mantissa bits are used, there will be a smaller interval size. Using the format in the previous figure, we can determine the most negative and most positive numbers as shown. The most negative number in the format is achieved by taking the sign bit, MSB bit as 1 to illustrate its negative, and remaining mantissa bits are all set to 0. And the exponent value is 0, 1, 1, 1. So 0 indicates is a positive value and the magnitude is 7. So this is the representation for the number -1 multiplied by 2 to the power of 7, whose decimal equivalent is -128. Coming to the most positive number, the MSB bit in the mantissa is 0 and the remaining bits are all ones. The exponent is the same as in the previous case. This yields the answer equivalent to 1 minus 2 to the power of -11 multiplied by 2 to the power of 7, whose answer is 127.9375. The smallest positive number is computed in a similar fashion by taking MSB as 0 and keeping all the remaining bits except the LSB as 1. And the power is taken to be 1.000, which indicates it is -8. So the equivalent of this is 2 to the power of -19. The exponent acts like a scale factor to increase the dynamic range of the number representation. Let us consider an example. So in this example, we are given a decimal number and this has to be converted into the floating number using the format specified in the previous diagram. So when you're given a value like this, 0.1601230, we initially scale it by dividing it by 2 to the power of -2 here so that we can obtain an exponent. So division will yield the value 0.640492 and the exponent is going to become -2. Now you can also have gone with other values also. So the other choices could also have been 0 or -1. You could have selected other exponent values also. So the number has now become, after this method, it is now 0.640492 into 2 to the power of -2. Since we want to take the exponent in negative, we have to take 2's complement. So under 2's complement notation, minus 2 is represented as 1, 1, 1, 0. Now, the mantissa is converted into Q11 format because the available bits for us is 11. So in Q11 format, the representation is something like this. In the initial position, we take the exponent, that is 4 places, followed by the remaining for the mantissa. So cascading these two together gives you the final representation. On similar lines, the second data is for a negative number. In the case of negative, here we are scaling it by 2 to the power of 5, and we obtain a value minus 0.638454. The scaling is an attempt to bring the value less than 1. Now, we can represent the number now as the mantissa into 2 to the power of 5. This conversion is not particularly unique because the other exponents could also be equally possible. Like for example, you could have taken 2 to the power of 6, you could have taken 2 to the power of 7, etc. Now, we will continue with the initial value that you considered. Now, the mantissa for the positive value can be expressed in Q11, and later we can take 2's complement to convert it to the negative. Hence, the result you obtain will be something like this. And the exponent similarly can also be represented. So the exponent is 0, 1, 0, 1 because the value is 5. It's a positive number. And later we cascade or append the representation of the mantissa. So this is how you can represent any given decimal number into its equivalent floating point form. Let us consider the arithmetic operations for floating point. Floating point arithmetic is definitely more complicated compared to fixed point. There are some rules to be satisfied to do manipulation for floating point. Let's consider the operation called as addition. To perform addition of two floating point numbers who are expressed as x1 and x2, carrying mantissas m1 and m2 respectively and exponents e1 and e2 respectively, the operation can be shown below. The first step is to make the exponents the same. So in that case, we compare the value e1 and e2, find out which is greater and make the smaller one equal to that value. This step is also known as aligning the exponents. So unless the exponents are same, we cannot perform addition. Therefore, the operation of addition x1 plus x2 can be denoted as m1 plus m2 times 2 to the power of minus e1 minus e2. In this case, we are assuming that e1 is more than e2. Therefore, the second exponent has to be adjusted. So to increase the value of e2, you can see that we are including the value of e1 also here. So minus of e1 minus e2 will be the new exponent after adjustment. Now, 2 times e1 is common for both, and it is common for both, hence it is taken outside the bracket. If suppose the value e1 is more than that of e2, it is the first case. If e1 is less than e2, then this time e2 is greater, so the common exponent will be e2. 2e power of 2 is taken outside, but we should not forget that we have to adjust the first exponent before we take out e2. Therefore, because we are taking this as a common, we have to subtract that value, hence we have minus e2 here. So clearly we can see this is a lot more complicated compared to that of regular binary addition or subtraction. Next, we consider the operation which is called as multiplication. Once again, we consider the number x1 and x2 which are expressed as m1 times 2 to the power of e1 and m2 times 2 to the power of e2. The mantissas are m and exponents are e. Now the mantissas individually are considered to fall in the range of 0.5 to 1. This is an attempt to prevent a sort of overflow. The calculation can be performed as shown here. The result is x1 into x2. We multiply the respective magnitudes and we add the exponents. So this is how we perform the operation, and the result may be expressed as m times 2 to the power of e. Here we have shown individually m is obtained by multiplying m1 and m2, e is obtained by adding the exponents e1 plus e2. Let us consider an example now for these arithmetic operations. First we perform the addition of two floating point numbers. The number which is shown here, we can see the number and its equivalent, and similarly we can see the second number and its equivalent. Now we require to do addition. Before we proceed for adding, we've changed the first number so that it should have same exponent as second number. Because the second number exponent is greater, we are adjusting the first one to be same as the second one. So after performing that addition, that change, the value will now look like something which is shown here. So we can see that the exponent has now become 5. And along with that, the mantissa part will also change. Now we can proceed for the operation called as addition. So taking those numbers, we can identify the mantissa parts. So the initial part is the exponent and the later part is the mantissa. So we take the mantissa alone and we add the mantissa. The addition here results in an answer which looks something like this, and the equivalent of that you can find. The equivalent can be found like this. Since the exponent is common, straight away we write the exponent to be equal to that of the greater value. So the exponent here is 0, 1, 0, 1. It is equivalent is plus 5. And here is the mantissa part. Now to find the magnitude of that, we can easily do a conversion. The answer we will get is negative of, see, the sign is taken to be minus because the most significant bit in the mantissa is 1, so it should be a negative number. So we take minus and we then multiply respective weights, and finally we multiply it by the exponent, which is 2 to the power of 5, and the equivalent you get answer is shown here, and after adjustment the answer turns out to be minus 20.265625. Coming to the operation of multiplication, so once again we are taking these numbers as shown in the example here. We individually find what are the exponents. So E1 is this, E2 is this, M1 is this, and M2 is this. Now we have learned that we have to add two exponents in the 2's complement form. So the addition of those two in the 2's complement form gives you the result 0011, which is plus 3. Now in the decimal domain, the powers, if you add, it is minus 2 and 5, we are getting an answer which is plus 3. So the answer is correct. As previously shown, when introducing the multiplication rule, when multiplying two mantissas, we need to apply their corresponding positive values. If the sign for the final value is negative, then we convert using 2's complement method. In our example, M1 is said to be this much, it's a positive mantissa. However, the second one, M2, is said to be negative mantissa. And since the MSB is 1, it is obviously negative. To perform multiplication, we use 2's complement to convert M2 to its positive value, that is shown here, and the multiplication result should be negative. So therefore, we multiply two positive mantissas and truncate the result to 12 bits to obtain the pattern which is shown here. Now this has to be converted to negative. It is done by taking 2's complement. So taking 2's complement of the result will give you a pattern which is shown here. This is the mantissa part of the result. Hence the product is achieved by cascading the 4-bit exponent followed with 12-bit mantissa, and converting this number back to decimal, we can check that the result is this. Let us talk about the condition which is called as overflow and underflow. When you are performing an operation, overflow will occur when the number is too large to be represented in the particular floating point number system. When you add two mantissa numbers, it may lead to a number which is more than +1 or less than -1. And multiplication of two numbers causes the addition of their two exponents. There also that exponent could overflow. Let's take examples. Case 1, we are adding two floating point numbers as shown here. The two exponents are same, so we don't have to worry about this, and the biggest positive number is a 4-bit 2's complement representation. Yeah, obviously in 4-bit that's the highest number, that is plus 7. So the exponent is plus 7. Now when we add the two positive mantissa numbers, the result that you get will be shown here below. The result from adding the mantissa number is negative. So you see the MSB, it is 1. We should treat it to be negative, and hence originally we had taken positive, but we are getting negative answer. Hence there is a overflow. In case 2, when we multiply the numbers which is shown here, adding the two positive exponents, that is 7 plus 7, we get an answer 1,000,000. Looking at the MSB, we think it's negative. That means that there is an overflow. If you multiply the two mantissas, there is no issue. Whatever answer we are getting, this is correct. The other situation we have is called as underflow. As we have discussed before, underflow will occur when a number is too small to be represented in that particular number system. Let us perform the operation of division. Two floating point numbers are given. If we divide it, first subtracting the two exponents leads to the result which is shown here. So this answer is positive. That means that an underflow has occurred. Okay, the sign bit is 1, but answer has a sign bit 0. So we know that it has changed, so it is having an underflow. If you divide the two mantissas, the division will give you a correct answer. However, in this case, the expected resulting exponent is -14 in decimal, which is too small to be represented in the 4-bit 2's complement system. Hence, underflow had occurred. Thank you all.